Welcome to Brain Vision.
We're going to repeat the previous problem, but now assuming we have isentropic efficiencies of 85% for both the pump and the turbine. So now we don't have, I should basically adjust my my chart here, which I forgot to do. Add in, these should be prime and prime. And now this should be coming down here. Well, let's say it stays saturated vapor. I'm not sure where it actually winds up. Did I actually calculate? 4 prime, 4. No, I didn't actually calculate where this state was because we didn't need it. And then this guy, kind of comes up with a little bit of a slope here, so it's very hard to see how that we'd have a point two somewhere up here, right? Where it's a little bit increased in entropy. So same situation, 90% for the isentropic. Well, no, actually, this whole problem, I drew that. I really shouldn't have drawn that like that because in this problem, it's this point that should be 4. And so let's see here. We need that should have some little more entropy than at 3. So this should be 3 here, right? And then 4 prime would be here because we still need that entropy. We still need the quality factor here at 4 to be 90%. So we'll basically wind up having to shift 3 in so that we have an increase in entropy going from 3 to 4. So this curve here should be gone. And likewise, let's see here. This would be the same. We'd wind up, at a point like right here instead of 2 prime. Okay, so that makes things better. So let's maybe clean this up a little bit if we can do it carefully. Get some rid of that. And there we go. And clean that up a bit. Okay, that looks better. So again, I'm glad I didn't do that because it shows you basically you have to shift 3 in so that you can get to 4, the same point, the same state at 4 as you did in the previous problem. Okay, now on to efficiencies we have. This is the same, but now the pump work is a little bit greater because it's not perfect. So that's really not going to change a whole lot about the answer because, again, this is a very small portion of what the actual power out is, or the specific work out in the turbine. But we can then get the enthalpy at state 2. We know everything at state 4 because we know the quality factor and the pressure. Now, what we have to do here is we have to start to kind of iterate here because what we want is we need the we need to make sure that there's various ways to iterate on this, but one way, and I should put primes on here, one way is to iterate on pick a T3 and because we don't know what this temperature is now. Pick a T3. Because we know if we know T3, we know P3, that will give us an H3 and an S3, which then we can figure out where this point would be because we know S3 or S4 prime is S3, right? And again, I copied some of this stuff over that I should not have from over here, right? Well, let's actually, let's keep those. And let's actually say that we have S2 prime equals S1 and S4 prime equals S3. So there. So now what we can do then is we can figure out the actual the quality factor at 4, the enthalpy at 4, and now we know the enthalpy at 3 and the enthalpy at 4, or 4 prime, and we also know the enthalpy at 4. So we can calculate the turbine efficiency, the thermal isentropic turbine efficiency. And that, if we pick a temperature here, we get about 81.7%. So that's too low. Okay, so if you kind of play around with this a little bit, you realize that to increase this, you need to increase the temperature, which isn't surprising because just for a Carnot cycle, you need to, the higher the temperature, the high temperature here, the more efficient it will be. So let's go up to 1,000 cal, or 1,000 degrees Fahrenheit. So let's see here. We do that, and we wind up with an enthalpy and an entropy at 3. Again, it's looking for the entropy at 4 prime is the entropy at 3. So then we can figure out the quality factor at 4 prime and the enthalpy at 4 prime. And we can see, then we can figure out, now that we know this, and we know that, let's see here, we know this, and this, we can figure out the efficiency, the efficiency of the turbine. And now it comes out to be about 87.3%, which is too high. So then we can interpolate. We can, say, okay, well, we want 0.85 in here, so we can figure out the proportions here, and then figure out the proportions between these temperatures. And it winds up being, if we interpolate, we get 958.4 degrees Fahrenheit. Now, if we use the software, we can get a little more accurate value. And in fact, I did that, and or you could kind of refine your interpolation a little bit. I did that, and I got actually 955.7 degrees Fahrenheit, and then the enthalpy at 3 would be 1,472.5 BTU per pound mass. So that's a specific enthalpy. Now we can go through and figure out the heat going in, the rate of heat going in, and that's about 130,000 BTU per second. The rate of heat flowing out is about 69,000 BTU per second, and the efficiency is now about 33.1%. So if we compare that to previously, we see we get a lower efficiency, as we'd expect, because we now don't have ideal pump and ideal turbine behavior. You can see this number is the same, actually, right? Well, no, it isn't the same. Well, yeah, it's not sure. Maybe I copied it down wrong. It's very close to being the same. Should it be the same? Out would be between 4 and 1. 4. No, it should be the same. I think I might have this should be maybe a 9, or this should be a 7. Anyway, it's a very minor difference here, because basically we kept these 2 points the same in both problems. It was this point and this point that got shifted. So a little less efficient, 33.1%.